Welcome to the Deep Dive. Today we're tackling something, well, truly epic. The Millennium Prize Problems. These are 7 incredibly tough mathematical puzzles. The Clay Mathematics Institute announced them back in 2000, right at the turn of the millennium.
That's right. Think of them as, I don't know, the Mount Everests of mathematics. Super challenging.
And there's a serious incentive, isn't there?
Oh, yeah. A cool US $1 million prize for the first correct solution to each one. It definitely gets people's attention.
It's quite the pot. And this whole idea, it has some history behind it.
Absolutely. It wasn't created in a vacuum. The Clay Institute was consciously looking back to David Hilbert.
Ah, Hilbert's problems from 1900.
Exactly. His famous list of 23 problems really set the agenda for a lot of 20th century mathematics. These Millennium Problems are sort of the 21st century version, carrying that torch forward.
Okay, so for this deep dive, what's our goal? What should listeners expect to get out of this?
Well, our aim is really to unpack what these problems are fundamentally about. Not necessarily the super technical details, but the core ideas, why they're significant.
And their impact.
Yes, and the impact they've already had and continue to have on maths and, even related fields.
All right, let's meet the contenders. Can you list the 7 problems for us?
Sure. We've got the Birch-Swinnerton-Dyer conjecture, the Hodge conjecture, Navier-Stokes existence and smoothness,
Okay.
the P versus NP problem, the Poincaré conjecture. That's the one that's actually been solved, we should say.
Right, the solved one.
Then there's the Riemann hypothesis, and finally, Yang-Mills existence and mass gap.
Wow, quite a list. And they cover a lot of ground, mathematically speaking.
Oh, absolutely. They touch on so many different areas. You've got algebraic geometry, number theory, mathematical physics, topology, theoretical computer science, partial differential equations. It's really a broad sweep.
It shows how connected everything is in modern math, I suppose.
It really does.
No, something I find interesting is that these weren't completely new questions when they were announced, were they? Unlike maybe some of Hilbert's.
And a key point, no, these were already, known major unsolved problems that mathematicians were actively working on.
So the Clay Institute basically put a massive spotlight and a big prize on existing grand challenges.
Pretty much, yeah. They identified these as fundamental questions whose solutions would be major breakthroughs.
And the official announcement, it was quite an event.
It was very formal. May 24, 2000, in Paris, at the Collège de France.
Prestigious venue.
Very. And announced by mathematical heavyweights too, John Tate and Michael Atiyah. It really signaled the importance the Institute placed on this initiative.
Okay, let's start with the success story then. The Poincaré Conjecture, it's the only one solved, the only prize sort of claimed. What's the essence of this problem?
Right. The Poincaré Conjecture is fundamentally about topology, about the basic shape of three-dimensional objects.
Right.
Think about a 2D surface, like the surface of a sphere. Any loop you draw on it can be smoothly shrunk down to a single point without leaving the surface.
Yeah, you can just pull it tight.
Exactly. The conjecture asked, if you have a closed 3D space without any boundaries, and every loop inside it can also be shrunk down to a point we call that simply connected, does that guarantee the space is essentially a 3-sphere?
A 3-sphere being like the surface of 4D ball.
Precisely. So is being simply connected enough to define the 3-sphere, topologically speaking?
That was the core question.
Yes. The precise statement is, any three-dimensional topological manifold which is closed and simply connected must be homeomorphic, that's topologically equivalent to the 3-sphere.
And there was a related idea about smoothness, too.
Yes. Later on, mathematicians developed a smooth version. It asks if such a manifold is not just topologically the same, but smoothly the same, diffeomorphic to the standard 3-sphere. It turned out the topological and smooth versions were equivalent in 3 dimensions.
So who cracked it? Who's the mathematician behind the solution?
That was the extraordinary Grigory Perelman, a Russian mathematician. He posted a series of papers online in 2002 and 2003 outlining the proof.
And it wasn't entirely out of the blue, method-wise. He built on previous work.
Oh, absolutely. Critical point. His work was really the completion of a program initiated by Richard Hamilton.
Hamilton's program using?
Ricci flow.
Exactly, Ricci flow. It's a type of geometric evolution equation, a system of partial differential equations. Think of it like trying to smooth out the geometry of a space over time, like heat flow smooths out temperature differences. Hamilton had the idea to use this to tackle the conjecture. and Perelman provided the crucial breakthroughs needed to make it work and overcome the hurdles.
A monumental achievement. And Perelman received significant recognition for it, right?
He did. He was awarded the Fields Medal in 2006, which is often considered the highest honor in mathematics.
But he famously declined it.
Yes, he did. He declined the Fields Medal. And then, in 2010, the Clay Institute offered him the Millennium Prize for solving the Poincaré Conjecture.
And he turned down the $1 million too. He did. He refused the prize money.
Why? What was his reasoning?
His stated reason was that he felt Richard Hamilton's contribution was just as important as his own, perhaps even more foundational to the overall proof. Since the prize was offered only to him, he felt it wouldn't be fair to accept it.
Wow. That's quite a statement about collaboration and contribution in science.
It really is. It sparked a lot of discussion about the nature of mathematical discovery and recognition.
A fascinating story indeed. Okay, so 1 down, 6 to go. Let's move on to the unsolved ones. First up, the Birch and Swinnerton-Dyer conjecture. What's this one about?
This one takes us into number theory, specifically looking at elliptic curves defined over the rational numbers. These are certain types of polynomial equations.
Okay, and the puzzle is?
The core idea is about understanding the set of rational solutions points on the curve whose coordinates are fractions. Does the curve have a finite number of these rational points or an infinite number?
And the conjecture proposes a way to tell.
Yes. It proposes a connection between that question, finite or infinite solutions, and the behavior of a complex analytical object called the L function associated with the curve.
An L function? Sounds complicated.
It is quite abstract, but the conjecture, specifically the Millennium Prize version, relates the rank of the elliptic curve, which is related to how many independent infinite families of rational solutions it has, to this L function.
How so?
It states that the L function, LES, should vanish, meaning it should equal 0 to a specific order, namely the rank R at the point S equals 1.
So an algebraic property, the rank, is predicted by an analytic property of this function.
Exactly. It's a deep connection between algebra and analysis. It's amazing to think that the behavior of this complex function at a single point could tell you something so fundamental about the number of rational solutions.
It's different from Hilbert's 10th problem, then, which was more about decidability in general.
Very different. Hilbert's 10th showed there's no general algorithm to decide if any Diophantine equation has integer solutions. This is much more specific, predicting a precise relationship for elliptic curves. Andrew Wiles, famous for Fermat's last theorem, actually gave the official problem description for Clay.
Interesting. Okay, next. The Hodge conjecture. This sounds pretty abstract, projective, algebraic varieties, Hodge cycles.
Yeah, this one definitely lives in the realm of abstract geometry. It connects algebraic geometry with topology and analysis.
Can you give us the gist?
Okay. Imagine you have a geometric shape defined by polynomial equations in complex projective space. That's your projective algebraic variety. Topology lets us study holes of different dimensions in this shape, represented by cohomology classes.
Right.
Some of these cohomology classes have special properties related to the complex structure. These are called Hodge classes. They are detected using analysis, essentially.
Okay, Hodge classes are special holes.
Sort of, yes. Now, you can also define holes in a purely algebraic way by looking at subvarieties, geometric shapes defined by polynomials living inside the bigger shape. These define algebraic cycles.
Algebraic versus analytic holes, roughly.
You could think of it that way. The Hodge conjecture proposes that the special Hodge classes, the ones found using analysis and topology, are actually just combinations of the algebraic cycles.
So the fancy ones are built from the simpler algebraic ones.
Precisely. It claims that every Hodge class is a rational linear combination of the classes coming from algebraic subvarieties. It's about showing that the underlying algebraic structure dictates these more subtle topological and analytic features. Pierre Deligne gave the official statement for this one.
Deep stuff. Let's switch to something perhaps more concrete. Navier-Stokes existence and smoothness. Fluids, right?
Exactly. The Navier-Stokes equations are the fundamental equations describing the motion of fluids. Water, air, oil, you name it. Incredibly important in engineering, physics, meteorology.
But there's a problem with them.
Well, a problem with our understanding of them, especially in 3 dimensions. We use them all the time. They work incredibly well in practice, but we lack a complete mathematical theory for their solutions.
What's the specific question?
The main question is, starting with some reasonable initial fluid state, do smooth, physically realistic solutions exist for all time? Or can the solutions develop singularities, points where velocities or pressures become infinite, where the smoothness breaks down? Think about turbulence. Does it arise from the equations themselves developing these pathologies?
So we don't know for sure if the math always behaves nicely.
That's the core issue. We haven't proven that smooth, globally defined solutions always exist under the given conditions, nor have we proven that they must break down. The challenge is to prove one or the other.
Can you remind us what the equation looks like, roughly?
Sure, it's duo plus uo plus giro. You have terms for how velocity changes in time, how fluid carries itself along convection, how viscosity smooths things out, diffusion, internal pressure forces, and external forces like gravity. Proving existence and smoothness for this beast in 3D is the challenge. Charles Veverman wrote the official statement.
Okay, moving into the computational world, P versus MP, this one comes up a lot.
It does, and for good reason. It's a fundamental question about the nature of computation and problem solving.
What's the basic idea? P and P.
Okay, P stands for polynomial time. These are problems that a computer can solve relatively quickly, where the time taken grows polynomially, like n squared or n cubed, as the problem size n increases.
Yep.
Think sorting a list.
Got it. And NP.
NP stands for non-deterministic polynomial time. This is a broader class. It includes all problems where if someone gives you a potential solution, you can check if it's correct quickly in polynomial time.
So checking is easy, but finding might not be.
Exactly. The question P versus NP asks, is every problem whose solution could be checked quickly, NP, also a problem that can be solved quickly, P? In other words, does P equal MP?
And the betting is?
The overwhelming consensus among computer scientists and mathematicians is that P does not equal NP.
Meaning there are problems easy to check but genuinely hard to solve.
Precisely. Think of factoring large numbers. Multiplying two primes is easy, P. But finding the prime factors of a large number seems hard, though checking if proposed factors are correct is easy, making it NP. If P and P, it would mean there's a fast algorithm for factoring, which would break most modern cryptography.
Huge implications, then.
Massive. Across cryptography, optimization, AI, biology, economics, you name it. Proving PANP, or unexpectedly PAENP, would be revolutionary. Stephen Cook formulated the problem in its modern sense.
Okay, nearly there. The Riemann hypothesis, another famous one, also from Hilbert's list originally.
That's right, Hilbert's eighth problem. It's arguably one of the most important unsolved problems in pure mathematics, especially in number theory. It's all about the distribution of prime numbers.
And it involves the Riemann zeta function.
Correct. The function and 1 to infinity of 1 sub sup. You plug in a complex number s and you get a value. This function equals 0 for certain values of s.
The zeros of the function?
Yes. There are some trivial zeros at the negative even integers, -2, -4, -6, and so on. But there are infinitely many other non-trivial zeros located in a specific strip of the complex plane.
And the hypothesis makes a claim about where these non-trivial zeros are.
It makes a very precise claim. It states that all non-trivial zeros lie on a single vertical line in the complex plane, the so-called critical line, where the real part of s is exactly 12.
Just 12, wow.
Yep. Billions upon billions of zeros have been calculated, and every single one found so far lies on this line. But proving it for all of them, that's the challenge.
And if it's true, why does it matter so much for primes?
If it's true, it implies a very strong, predictable pattern in how prime numbers are distributed. It essentially gives the best possible estimate for the error term in the prime number theorem, which approximates how many primes there are up to a certain number. It suggests a kind of hidden regularity in the primes. Enrico Bombieri wrote the Clay exposition for this one.
Fascinating. Okay, the final problem. Yang-Mills existence and mass gap. This sounds like physics.
It is. It bridges mathematics and fundamental physics, specifically quantum field theory. Quantum Yang-Mills theory is the mathematical framework underlying the standard model of particle physics, describing the strong and weak nuclear forces.
And the mass gap, what does that refer to?
In quantum field theory, the vacuum is the state of lowest energy. The mass gap is the idea that there's a minimum positive energy difference between the vacuum and the next lowest energy state.
Like a minimum energy required to create a particle.
Essentially, yes. It corresponds to the mass of the lightest particle predicted by the theory. If there's a mass gap, the lightest particle isn't massless.
So what's the problem with Yang-Mills theory?
Well, classical Yang-Mills theory describes massless particles, think gluons, the carriers of the strong force. But experimentally, we don't observe free gluons. We see them confined inside massive particles like protons and neutrons. This is color confinement. This suggests the quantum version of the theory should have a mass gap.
But it hasn't been proven mathematically.
Exactly. The challenge has two parts. First, rigorously prove that a mathematically consistent quantum Yang-Mills theory actually exists in our four-dimensional spacetime. This involves satisfying certain axioms, like those laid out by Whiteman or Osterwalder Schrader. Second, prove that this rigorously constructed theory exhibits a mass gap, 0.
So establish the theory on firm mathematical footing and show it predicts massive particles matching reality.
That's the essence of it. It's about bridging the gap between the physicist's successful use of the theory and a complete, rigorous mathematical foundation. Arthur Jaffin and Edward Witten provide the official statement. It involves concepts like asymptotic freedom, too, which suggests the theory behaves well at high energies.
These are clearly immense challenges. How did the mathematical community react when these prizes were announced? Was everyone thrilled?
It was definitely a mix. Some were very positive. Andrew Wiles, for instance, hoped the prize money would help popularize the problems, get more people excited about mathematical challenges.
Make math seem less intimidating, perhaps.
Maybe, yeah. And Elaine Kahn saw it as a way to counter the idea that computers were taking over math, highlighting the need for human insight.
But there was pushback, too.
Oh, yes. Some prominent mathematicians were quite critical. Anatoly Vershik, for example, called it show business.
Show business? Why?
He felt it focused too much on the spectacle and the money, arguing that direct funding for research programs and young researchers would be more beneficial to mathematics itself. He also noted how the media often just focused on the $1 million, missing the deeper substance.
That's a fair point.
Xintong Yao echoed similar concerns, even being critical of foundations seeming to appropriate or take ownership of these fundamental questions that mathematicians were already working on. So definitely not universal acclaim. It highlighted different views on how math should be supported and communicated.
Interesting dynamics. Okay, as we wrap up this deep dive, what's the big picture takeaway on the Millennium Prize problems?
I think the key takeaway is that these represent some of the deepest, most fundamental questions we face in mathematics today. They cut across diverse fields, linking seemingly disparate areas.
And they are hard.
Incredibly hard. The fact that only one, the Poincaré Conjecture, has been solved in over 2 decades really speaks volumes about their difficulty. They truly push the limits of current mathematical understanding and techniques.
But the effort isn't wasted, even if they remain unsolved for now.
Absolutely not. The work done trying to solve these problems often leads to major advances in itself. New theories, new tools, new connections between fields. They act as powerful engines driving mathematical progress.
So, a final thought for our listeners to ponder. We've talked about the 6 remaining unsolved problems: Birch and Swinnerton-Dyer, Hodge, Navier-Stokes, P versus NP, Riemann hypothesis, and Yang-Mills. Which one captures your imagination the most? Thinking about the potential impact. It's fascinating to consider which breakthrough might change our world the most profoundly.
A great question to think about.
Thanks for joining us on this deep dive.